Thank you very much for the invitation. I'm sorry that I can't be in Trento due to teaching here in Potsdam, but I'm glad that at least I can join remotely some of the talks, or most of the talks. And I'm sure that you already had great discussions even at Trento. So I will continue with discussions or talks or ideas that was brought up again already in a few of the presentations, focusing on binary neutron star mergers and how we can use them as multi-messenger laboratory. And of course, this is directly the title of the, let's say, workshop. And I want to go one small step further, namely in discussing where do we actually get our information from. I think this was covered in a lot of talks and in much more detail than I can do this today in just 25 minutes. But I also want to put this in relation to actually which messenger and which channel and which idea or computation provides us, let's say, information about dense matter or supranuclear dense matter in which density region. And this plot here is from Peter Pang from NICEF, where you see a variety of equations of state. Where these equations of state come from does not matter so much, but these, for example, were provided by Ingo, so one of the organizers. And you see a variety of equations of state, and we, of course, want to find the correct equation of state describing the interior structure of neutron stars. And we all know that we can relate a microscopic equation of state to macroscopic properties through the Tolman-Oppenheimer-Volkoff equation. When we just solve for these equations, we get basically a one-to-one relation between pressure density curve and the mass radius curves of neutron stars. And therefore, observing neutron stars is a very good and very neat idea. However, the point is that different channels or messengers will provide us information at or up to different density regions. So if we start at small densities, small of course in quotation marks, up to twice nuclear saturation density, then we have the possibility still to use nuclear physics computations, or also heavy ion collision experimental data, for example. There will be a talk tomorrow about this by Sabrina Hus. And these densities, or these, let's say, information are provided up to twice nuclear saturation density. So still densities beyond what we currently have in an atomic nuclei, but not as extreme as in neutron stars, for example. Because if we want to probe densities that go beyond this, let's say 4 or 5 times nuclear saturation density, then what actually happens is that we have to look at neutron stars. Inside a neutron star, of course, we probe densities up to the central density of a neutron star, which easily can reach 4 or 5 or 6 times nuclear saturation density, depending mostly on the mass of the neutron star. If we, for example, look at, I didn't list this here, but on radio observations of massive pulsars, then of course we probe higher densities than during the Inspiral by gravitational wave signals, where we have most of the time neutron stars 1.4, 1.5 times the mass of the sun as most. If we then go beyond this and, for example, look at electromagnetic signals that are emitted after the merger of two neutron stars, then this actually proves or probes even higher densities several times nuclear saturation density, 6, 7, 8 times. And one has to be honest, this is actually the most extreme scenario that one can have, because if one would increase the density even further inside this small region of space-time, then you easily form a black hole. And this is, as most of you know for sure, is also what happened with GW 17817. There was a black hole very likely formed after the merger, which of course gives us an upper bound on where the equation of state can still be probed in astrophysical observatories. And these different parts, of course, now have to be combined in particular ways. And I want to show here works that we did. And of course, this is a bias just towards our work, how we combine these multi-messenger information in a coherent way to get most science out of this. But I clearly want to emphasize that other groups are doing similar things, right? Other groups, and this list here is not complete, are also developing multi-messenger frameworks, are also trying to connect multiple, let's say, observational information, nuclear physics informations. And of course, all this goes in the same direction. And I will focus here on the work that we have been doing over the last roughly 2 years to really use neutron stars and neutron star measurements as laboratory for supranuclear dense matter. So what we do is actually a multi-step procedure where we start with, again, nuclear physics computations. So we use chiral effective field theory computations up to roughly 1.5 times nuclear saturation density, which would be around here in this plot. And beyond this, we use a very general speed of sound extrapolation, which allows us, you see this potentially here, I don't show how good the screen is, you see these straight lines, which allows us also to incorporate, for example, phase transitions. So we have a rather big set of equations of state. In fact, it doesn't matter how many equations of state you pre-compute. You can use a few thousand, you can use 100,000. Numbers don't matter here. What is important is that you have actually a large enough set that you can realistically span the parameter space that you want to cover. And you should incorporate the most physics that you can incorporate, and also up to a point where you still have uncertainty measurements. And therefore, for example, we stopped using chiral effective field theory at 1.5 type nuclear saturation density and didn't go beyond, simply because uncertainties will get larger. And then, of course, as I said, these computations are our starting set. We use this set of equations of state now to incorporate, for example, maximum mass measurements of single radio pulsars. And we had a very nice talk about this already, about measuring high mass neutron stars, mostly through Shapiro time delay. These are very accurate measurements, and these very accurate and very precise and important measurements actually provide us typically a lower bound on the maximum mass of neutron stars, simply given by the fact that we have observed these neutron stars, which means the equation of state has to support them. If you look here in the background a little bit, you still see these equations of state, and you see that this purple band, actually this constrains the maximum mass, and the lower bound comes from actually these radio pulsars that have been observed. You also want to constrain the maximum mass from the upper side. So you want to put constraints on the upper bound of the maximum mass of neutron stars. And of course, you can't do this by observing neutron stars, right? This will always provide you with a lower bound, but you can do this by finding that a neutron star actually collapses to a black hole, or if you assume that the neutron star mass distribution or black hole mass distribution would be distinct from each other, you can also do this from single black hole measurements. However, this would be an assumption. If, on the other hand, you see, for example, a binary neutron star merger, and inside such a binary neutron star merger, you have clear evidence, and this was pointed out by Metzger, Zoller, and others, that there is clear evidence that actually GW78817 produces a black hole surrounded by a disk, supported by the electromagnetic observation. Then this gives you a maximum bound, or an upper bound on the maximum mass of neutron stars. And this is what we show here. So this is a combination on the lower bound from the massive pulsar measurements. And on the other side, we have the combination that we say that for large masses, we formed a black hole in GW78817. If we statistically combine this, then we find that we have a probability distribution of the maximum mass of neutron stars. And this is our first input. We already here use radio information, more or less single stars. We use gravitational wave information and kilonova information to get this maximum mass bound, which then is color-coded again here in purple. And you already see that some of the equations of state which you just started with will be ruled out or disfavored. Ruled out is actually a slightly wrong word, because we don't use hard cuts or anything, which means that every equation of state gets just a probability how likely this is, and gray just means that it's very unlikely. However, there might be a tail that actually expands up to higher radii. The next steps that one can incorporate, still looking partially at single neutron stars, would be the NICER measurements. Also there we had nice talks already, so I don't want to go into the detail. What you do with NICER, you all know this, you observe single neutron stars and you try to observe the X-ray pulse profile from these single neutron stars. And the fact is that the more massive the neutron star is, the more the neutron star will actually deform space-time. And a high mass neutron star will allow you to actually look slightly behind the neutron star. So it will appear larger, you will see a different pulse profile. And if you now do Bayesian inference, where you adjust the hotspots on the neutron star, just the size of the neutron star and the mass of the neutron star, then you get what is shown here, these ellipsoidal shapes, because you can rather accurately measure the mass with this radius, but not the individual component. And then these are the two, let's say, mass radius constraints from the nicer observations that if you incorporate them on top of what we've done before, you get a slighter peak around, let's say 12 kilometer radii of a neutron star. But luckily we can still go on with our interpretation and now come to gravitational waves. Also there we had already a presentation by Jocelyn and others where it was discussed how you use gravitational wave measurements to constrain the equation of state. Mostly this comes, of course, from measuring tidal effects. Here we redid the analysis with different waveform models that was not before used by LIGO-Virgo, but showed consistent results. And you see here, these two blobs are actually referring to the more massive neutron star and to the less massive neutron star. And you see, again, the error slightly decreases if you incorporate this measurement with the radii, and you start seeing a clearer picture and peak. Just as a point, what is very important in gravitational waveform analysis is, of course, waveform models. Sebastiano touched on this slightly on Monday, where so far for analyzing binary neutron stars, we either use more or less effective one-body approach, where you remap the relativistic two-body problem into an effective one-body problem, so you have an effective metric and a point particle moving around. You can speed this up, otherwise it would be very slow, but it can be used. It wasn't used in a lot of analysis, but it can be used by additional techniques. Or you have the possibility of phenomenological models that just provide a, let's say, well-guessed fit to post-Newtonian effective one-body NNR data to then describe the merger, describes the waveform up to the merger, but not beyond. And I want to highlight one of these studies about systematic uncertainties. Also, this was partially shown on Monday, was another study. The conclusions are rather similar, and I think are very important to keep in mind. This here is a study of an injection set, which means that the people used one particular waveform model, actually a phenomenological waveform model, which is given here in these blue dotted points. I think the details, which model and so on, doesn't matter so much. And then they simulated 39 different sources and injected these sources and analyzed everything with a variety of different waveform models. 4 waveform models are given here with different colors. And you see that step by step, of course, the radius measurements, because we will come also in the future, right? This is a look into the future. We will combine multiple measurements just from gravitational wave observations. And therefore, our radius measurement will be tighter and tighter. And you see that, for example, for the injected model in blue, we would recover very nicely the true injected radii after, let's say, tens or here 39 discoveries in terms of gravitational waves. However, the other models show systematic shifts away from the ejected ones. This is expected because every model has slightly different physics, every model uses different NR waveforms for calibration and so on. So there are uncertainties inherent in each of these models. The point is that if you have either a sufficient loud signal or a sufficient number of signals, you see here, for example, that our radii measurement for this, let's say, orange dotted model would be way off from the real measurement. Consequently, systematic effects, while currently we have only 1 or 2 gravitational wave detections for binary neutron stars, are well within systematic uncertainties. This will be different in the future. And this injection campaign here was done with the O4 sensitivity curve. So from the next observing run, it's unlikely that we will see 30 or 40 signals in the next observing run. But still with advanced LIGO, in at least the 5th observing run, we will see this amount of signals with even higher sensitivity. So the systematic effect is nothing that just will appear with the Einstein telescope. It will already be of importance for the advanced LIGO era. And no matter what, the important point is that if you really analyze current data, and I refer there to the talk of Jocelyn, and this is an analysis from the LIGO-Virgo collaboration, you see that actually the constraints on the, let's say, individual tidal deformabilities of the individual neutron stars They are in line with each other using different waveform models. Systematic effects currently are smaller than statistical ones. At least this is our interpretation. It's of course very hard to quantify this, but so far we don't have to worry about the systematic effects, but we will have to worry on a 1-2 year timescale. Moving on from gravitational waves to the next multi-messenger source, we partially use the kilonova already to determine the maximum mass of neutron stars. But of course, we can also directly, on a quantitative level, analyze kilonova signals. What you see here is the observed kilonova AT 2017 GFO that was in coincidence with GW17817. And you see here the observational data in the ultraviolet, green, red band, and so on to higher frequencies, higher wavelengths going down. And what you can now do is similarly to gravitational wave analysis, you use a Bayesian inference framework where you basically try to find, really with parameter estimation, the best matching light curves that fits all your data points. Therefore, it's so great that actually AT 2017 GFO was observed with so many telescopes. If you want to do parameter estimation with light curves, you can either use analytical models, which are sufficient fast, or partially semi-analytical models. If you want to go a little bit beyond this, what we did, we used full radiative transfer simulations. These actually, each light curve take about a week to compute, which means you can't use them if you really want to find the best matching template, because you have to evaluate maybe 1 million, 100 million or so of these light curves to really do the inference correctly. So what we did, we pre-computed the light curves for a set of initial configurations for the ejector properties, several thousand. Then we created interpolants, and these techniques are actually borrowed from gravitational wave astronomy, either through Gaussian process regression, or we also trained neural networks that within milliseconds can then, for arbitrary ejector geometries and properties, compute the light curve. And this allows you then to put this in a Bayesian inference code and get the ejector properties. And then you can link this actually to get, with numerical relativity predictions, the properties of the binary. And here it's nice that actually the electromagnetic observation of the kilonova are complementary to the measurement of the gravitational waves. This means that this time you actually rule out small tidal deformabilities. Qualitatively, this comes from the fact that you have observed a bright EM counterpart. You would have not done so if there wouldn't be enough ejector, and you don't create enough ejectors. The neutron stars are either too massive or very, very compact. And furthermore, the study also emphasizes that it was very likely that there was not an extremely high mass ratio. Just from the kilonova interpretation, you find results that are very consistent with the analysis of the gravitational waves. And of course, you can fold this in and get again these two blobs from the binary neutron star measurements, just from the kilonova analysis this time, where you have the more massive neutron star, the less massive neutron star, as for gravitational waves. And we all know that GW17817 was a great signal, but it was not the only binary neutron star system that was observed. So also 1904-5 was observed. The key property here is that the masses are significantly higher than for GW17817, which also made it much harder to actually find tidal effects. Here's a numerical relativity simulation of this, and you will see that, of course, there's an emission of gravitational waves. So the orbit will shrink, and you will see that very late, you just see tidal deformability. So you see deformations of the star at a very late stage and much smaller than for GW17817. In fact, there was not really an additional information coming from this observation beyond what we knew from 17817. Important is that NR simulations and also the analysis is completely in agreement with the fact that the amount of ejecta was very small, and therefore it is also consistent that we have not seen an electromagnetic counterpart for this event. One has to admit that it also was much harder to do the follow-up campaign, simply because the sky area was much larger. It was more or less a single event trigger or single detector trigger, but everything is consistent that we have not seen a counterpart for GW19425. And nevertheless, you can incorporate the gravitational wave information and finally get a result of the radius of a neutron star of about 11.9 kilometers. So this is a procedure and approach that I just described. So you do a step-by-step analysis where once at a time, your result is an input for the next time, acts as a prior, and then you stack these informations up. Again, I refer to the talk by Sabrina tomorrow. What you can in principle also add are heavy ion collision information. So for example, gold ions that you smash together, this can be added in addition, decreases the error slightly and gives you an even more concrete picture and idea about what is happening in these macroscopic and microscopic collisions. What I also want to emphasize is that what I showed now was where these first steps that we actually did for creating really a nuclear physics and multi-messenger framework. This is more or less a PhD thesis of Peter Pan, who developed this framework. It's public available at GitHub. So everything that I just described is available. You can download this. And the good thing is you can even do more than what I just described, because recently it became possible for us to not just do the sequential approach, but do a simultaneous analysis of gravitational wave data, of kilonova data, and in addition also for the GRB afterglow. So what you now do is you take a sample for masses, spins, orientation, and so on. So binary neutron star properties. You compute the expected light curve. You compute the expected GRB afterglow, so electromagnetic signals and the gravitational wave signal. You create a joint likelihood function, and then once at a time, you analyze all the signals at once for a given sample point. And of course, you have to do this again a few million times, which means that given that the parameter space is massively increased because you have to analyze more, let's say, given data, this also means that the computational resources get larger, that you need to do this. So if you do a full study from gravitational waves, GRB afterglow, and kilonova, then this needs to run on a supercomputer and roughly takes, let's say, around a week, a bit more than a week actually. If you, for example, remove the GRB afterglow, it just takes a few days. If you remove the gravitational waves, you can even do this in a day in a supercomputer. So it's very flexible in a way that you don't have to analyze all the data at once. You can use individual pieces, or you can use everything at once. And if you do so, then looking, for example, at this line, and the results that I showed you earlier were actually the one from Dietrich and Tood. If you now use this NMA frameworks, the nuclear physics and multi-messenger framework, you see that while the final result is all consistent with each other, it would be a problem if not, because this would mean that somebody is either wrong or uncertainties were claimed too small. You see here that actually uncertainties noticeably decrease compared to the other things. This comes from different things and different improvements. Once you have this joint likelihood function that we also changed for the EM analysis, you avoid KDEs in between of every step, and you really break some of the degeneracies that existed before when you do the simultaneous analysis here at once. And what I find very nice is here really that you do basically one parameter acceleration run to do a lot of interesting and cool physical aspects. So you can do nuclear physics constraints to the radius measurement, and for this talk focus on this one. Of course, you also get the chirp mass and information about the gravitational signal. You get the information about how much matter gets ejected. So this is very important for heavy element formation and creation. You understand the GRB central engine by the GRB afterglow. You measure the distance, which is important for the measurement of the Hubble constant, and you break again degeneracy, so you have the possibility to get a much tighter constraint for the Hubble constant, for example, than for individual measurements if you want to just use gravitational waves. With all this being said, I also want to give an outlook, and this is very nice work here recently by Colombo et al., where they compute how likely it is that we'll see X amount of gravitational wave detections, mostly binary neutron stars, in 04. And you see here, I highlighted this column, that there will be, let's say, a few, 8, maybe 10 or whatever, binary neutron star events in the next observing run. And let's say 50% of them, a bit less, depending on what observatory you use, will have an observable kilonova signature. It will be unlikely to see a GRB again and the GRB counterpart or afterglow, but we can expect in the next observing run from LIGO and Virgo to actually see a few, maybe 1, maybe 2, maybe 3, multi-messenger binary neutron star signals. And this is pretty cool. This plot here, I didn't find it an updated version, has to be updated because the next observing run for LIGO got a little bit delayed. It will happen now or start in March. But then there will be one operation, a 1 year operation, where it's very likely that you see these kind of sources. And if you go to the Einstein telescope, then of course, we will see hundreds or hundred thousands of these signals per year. And the good thing is there are a huge amount of other facilities, CTA, SKA, Ultrasat, and so on, that will come online during this time frame. So there would be really the possibility to study neutron stars, neutron star mergers in much more detail and to really pinpoint information for the equation of state. This would be all from my side, and thanks a lot for listening.